Hello, my name is Patrick Pfeiffer. My teammates are Mike Cunney, Randy Earl, Ryan Martinez, Schuyler Mann, and Terence Costigan. Our advisors are Chuan-Wang and Kevin Kolvenbach, and our stakeholder is Dana Jones from Accessadoor Inc. And our Senior Design 2 project is a gyroscopic self-balancing mechanism. The goal of this project was to design a self-balancing gyroscope with the intention to help aid those with neuromuscular disorders. The self-balancing mechanism is comprised of a self-driven flywheel acting as a gyroscope attached to a 2 degree of freedom rotating body. Actuators were attached to either side of the flywheel to allow for a more swift and controlled precession rate. Using these components together, the user of the mechanism would experience a secure force to counteract any imbalance they have.
Upon completion of Senior Design 1, a thorough analysis was conducted for the first prototype. Due to how the system was being driven via the rollers, as well as the large ball bearing, there was a lot of noise and vibrations within the system that created issues for the accelerometer readings. In addition, since the design was larger, there was a higher cost for electronic components, especially the actuators, that was outside the group's budget. For these reasons, as we headed into Senior Design 2, the group decided to pivot and develop a quarter scale model that would act as a proof of concept to showcase active gyroscopic precession. Since the design was smaller, it allowed for a reduction in the noise and vibrations, as well as the capability to 3D print many of the components within the design.
Design 2 incorporates many of the same features as Design 1, but it's been improved through frictionless joints here and here. These joints are made up of pillow block bearings, 3D printed housings with bearing inserts. The arm itself is a combination of aluminum extruded parts, brackets, and fine thread hardware. The housing is a 3D printed cage with a top plate, bottom plate, and midsection pinched together by a total of 10 bolts. The flywheel itself is housed inside of this cage. It is a steel flywheel of about ½ pound, connecting both motors with a steel shaft. Both motors on opposite sides of the cage promotes a symmetrical design, splits the torque, and allows for higher speeds.
The electronic system of the final design is composed of 3 main components which are governed by Arduino programming software. The process is structured around 2 main states which are governed by holding a button for 1 second. A reactive state where, based on the angle reading of the accelerometers, the actuators extend to respond to falling motion and precess the gyro. And then a non-reactive state where the actuators are homed and don't respond to changes in the angle to allow someone to bend over without stabilization torque acting on them. As you can see here, as the structure or person falls, the accelerometer triggers the actuators to precess the gyro, which is supply a stabilization torque opposite of the falling motion. The goal is to control the precession with the actuators to control the stabilization torque.
Because of how we wanted our system to interact, we had a couple of things we learned from our first prototype that included a lost microcontroller and a couple lost motors due to overvoltage. Those lessons led to design decisions in the form of a motor driver shield using an H-bridge configuration, microcontroller power management through that same shield, and also an actuator home with an on-demand button with user feedback with a single LED. With respect to the H-bridge design for our current purposes, the design did allow us to use the multiple chained MOSFET to both handle extra current and higher temperatures, as well as allowing for better spin up and spin down characteristics and quicker prototyping overall, as it was a single unit as opposed to a solution designed in situ. Furthermore, the actuator's power coming through the Arduino's 5-volt pin would initially be a problem due to the low current output. However, due to the motor driver's supply voltage to the Arduino, it allows for higher current output for the actuator's movement. Overall, the solution was more elegant and allowed for more rapid prototyping.
So, based on what Schuyler, Mike, and Randy said, we were able to integrate our electric, mechanical, and software systems all into one. And we got our final design. So this was able to prove the concept of active precession using linear actuators, and the smaller design allowed to reduce vibration and noise, as well as reduce the cost of all the electronics and assembly. We also integrated a switch for desired movement, so that switch allowed us to turn on and off the actuators when we wanted to. The weaknesses of this final design were that we could only stabilize in one plane of motion, and in addition, the actuators were acting too slowly to the natural falling rate of the gyroscope. As you can see in this video, you can see that Randy is actually controlling the actuators more directly with the accelerometer, and this allowed him to do a bit faster stabilization of the actuators, but it was still not fast enough. So with that being said, for our future improvements, we want a stepper motor gimbal design, so we want stepper motors directly attached to the gyroscope at the pivot point. This would allow direct torque transfer as well as faster reaction time. We want multiplanar stabilization instead of singular one direction. We also want to implement it on a person's body, so this means make it bigger and have a battery powered system on it so that the person can walk around and be mobile the whole time. With that being said, thank you for watching and have a wonderful evening.